In the winter of 2012, in a basement scanning room at a Baltimore hospital, a medical illustrator pushed a dead owl into a CT machine and went very quiet. By the end of this, you'll see how this bird wrings its head almost all the way around without tearing the arteries that feed its brain, and why, by every rule of human anatomy, it should drop dead the instant it tries. The owl on the table had died of natural causes. Its body had been donated to a lab that normally scanned human patients for strokes and aneurysms. The illustrator, working alongside a neuroradiologist, wanted to know one simple thing. When an owl snaps its head over its own back, what happens to the blood vessels in its neck? In a person, that motion is dangerous. Whip the head around hard enough, and the arteries threading the spine can crimp, tear, or throw a clot straight into the brain. Surgeons see it in car crashes and chiropractic accidents. Yet owls do this casually, hundreds of times a day, for a lifetime, and nothing goes wrong. The scanner hummed. The first images came up on the monitor, and the numbers made no sense. The lab sat inside the Johns Hopkins Medical Complex, a place built to study the human skull, not a bird's. Its scanners and dye injection rigs existed to map the delicate arteries that wind up the human neck and into the brain, the same vessels that, when they tear, cause some of the most sudden strokes in medicine. For years, doctors there had treated those injuries as a hard ceiling on how much a neck can move. Turn your head too far, too fast, and you gamble with those arteries. That ceiling is why the owl was such an affront. An owl carries its eyes in fixed tubes. They cannot swivel in the skull the way ours do. To look behind itself, the bird has no choice but to rotate the entire head, again and again, far past anything a primate neck would survive. Everyone knew owls did this. No one had looked carefully at how the plumbing held up. And the strangest part isn't the bones at all. It's what the arteries do, which no one saw coming until the very last scan. Before any of that, though, someone had to decide the question was worth chasing. The chase fell to two people who barely overlapped in expertise. One was a medical illustrator named Fabian de Koch Mercado, trained to draw the human body with surgical accuracy. The other was Philippe Galeloud, the radiologist who ran the hospital's vessel imaging work. The illustrator had a hunch that an owl's neck was hiding something worth drawing, but a drawing is only as honest as the dissection behind it. So they gathered specimens. 12 owls in all, snowy owls, barred owls, and great horned owls, every one of them already dead of natural causes, became the subjects. Their method borrowed straight from the human stroke ward. They injected a colored dye into the arteries to stand in for blood, the same trick used to light up a patient's vessels on a scan. Then they ran the birds through the CT machine, slice by slice, and afterward opened the necks by hand to confirm what the images showed. They were looking for the failure point, the spot where, in a human, the artery would pinch shut under that much rotation. They expected to find fragile vessels barely surviving the strain. What the dye revealed instead was the opposite, and it started at the bone. An owl's neck bones are full of holes far too wide for the arteries inside them. That was the first thing on the screen that didn't fit. In almost every animal, the artery climbing the neck runs through a snug bony canal. In a human, the hole and the vessel are nearly the same size, gripping it like a ring. In the owls, those canals were cavernous. The vertebral artery passed through openings roughly 10 times wider than the vessel itself, leaving a generous cushion of empty space all around it. At first it looked like a mistake, a measuring error. It wasn't. There was more. An owl's neck holds 14 separate bones, while yours holds only 7, and the artery did not even enter the spine where it does in other creatures. It slipped in higher up, skipping the lowest bones entirely, which left the vessel unusually long and loose for the distance it had to cover. Slack, in other words, built-in slack, in a place where slack should be impossible. Every detail pointed the same way. This neck had been engineered to let something move that, in any other body, would be locked down tight. But slack alone could not explain how the brain kept its blood when the head came all the way around. Slack explained the bones, but it created a new problem the team couldn't ignore. When an owl cranks its head far to one side, the rotation can still squeeze the arteries on that side nearly shut. The scans showed it plainly. For a few seconds at the extreme of the turn, blood flow up one channel can drop toward nothing. In a human, that is precisely the recipe for disaster. The condition even has a name in the stroke ward: vertebral artery dissection, where the vessel wall splits under exactly this kind of twisting load. The brain and the eyes cannot simply pause and wait. Nerve tissue starved of blood begins to die in minutes. So the slack and the wide bony canals, impressive as they were, only deepened the mystery. They let the neck turn without crimping the artery against bone, but they did nothing to keep blood flowing to the head once the vessel pinched shut at the far end of the rotation. The illustrator kept coming back to the same wall. The anatomy that should have killed the bird was right there on the screen, and yet the bird lived. Something else had to be feeding that brain. The answer was sitting just under the jaw, and they had nearly scanned right past it. An owl's arteries balloon open mid-turn, pooling blood like tiny reservoirs under its skull. That was the piece everything had been missing. Where the vessels reached the base of the head, just below the jaw, they did not stay the same width like a human's do. They widened into small pouches, and when the team filled them with dye, the pouches swelled with reserve blood. As the head rotated and the lower artery pinched shut, those pools kept feeding the eyes and brain, a few seconds of stored supply to cover the squeeze. And there was one more thing. A small connecting vessel linked the artery systems on each side, so if one route closed, blood could cross over and arrive by another road. Together it formed a backup nobody had drawn before. This is the answer to how a bird can wring its head most of the way around and feel nothing. An owl turns its head roughly 270 degrees. You can manage about 90 before it hurts. The difference was never muscle or daring. It was plumbing, oversized bone canals, slack vessels, blood reservoirs, and a crossover line, all working together so the head could go where the eyes never could. The images the two men produced did more than settle a curiosity about birds. In early 2013, their work won a national prize for scientific visualization, and the drawings spread into textbooks and stroke wards alike. Doctors who spend their careers on the fragile arteries of the human neck found themselves studying an owl to understand what a blood vessel can be built to withstand. The bird had quietly solved a problem that still injures people every year. None of it was a trick or an exception. It was the plain result of a neck designed around a single demand, that the head must turn when the eyes cannot. Look at an owl swivel its gaze across a dark field now, and you are watching the most over-engineered neck in the animal world do something that, on paper, should not be survivable at all.